welcome to Chapter 26e, Relativity, Momentum, and Energy. And of course, we're going to be solving problems of relativistic momentum and energy. First up is relativistic momentum. So the law of conservation of momentum is still valid at high speeds if we put an additional term in here, a term that's called gamma p. Gamma p is the Lorentz factor for a particle. The p just emphasizes that this is about a particle, not for a reference frame. So momentum is gamma p times mass times velocity or speed. And note that p goes to infinity as u goes to c. So as you approach the speed of light, the momentum approaches infinity. So there's a cosmic speed limit. Consider a particle subjected to a constant force, such as a rocket that never runs out of fuel. If the force is constant, and we can see from the fact the force is the time rate of change of momentum, that the momentum is p equals force times time. And as the p approaches infinity, the speed will approach c, but never exceed it. So in other words, here we have speed versus time. Here's the speed of light. Here's the Newtonian velocity. But because of gamma, the speed of the particle can approach c, but never exceeds it. There is a cosmic speed limit. Consider two causally related events. A causes B. If A causes B, then it must be the case that TA must occur before TB. So TA is less than TB. So in other words, event A has to happen first. Suppose that there exists some kinds of causal influence between A and B that can travel at the speed u greater than c. In this case, we can use Lorentz transformation to show that there exists a reference frame S prime in which TB prime is less than TA prime. In S prime, event B occurs before A, even though A causes B. This would be like you being born before your mother was born. The dark side of this is you could kill your grandmother before you were born, and then you would never be born. So the principle of causalogy says no causal influence of any kind, particle wave, or even information can travel faster than the speed of light. Now, relativistic energy is the next topic. A particle moving at speed u conserves relativistic momentum in p in all reference frames as long as outside forces do not act. But there's another conserved quantity, the relativistic energy, E equals gamma p mc squared. Or gamma p is our Lorentz factor, 1 over the square root of the quantity 1 minus beta squared. The total energy of the particle may be then written as E equals gamma p mc squared, which is E naught plus k. That is the rest energy plus the kinetic energy. The total energy then consists of the rest energy, E naught equals mc squared, E equals mc squared, and the relativistic kinetic energy, which is k equals gamma p minus 1, that quantity, times mc squared. So it equals the quantity gamma p minus 1 times E naught. Now the relativistic kinetic energy is the quantity gamma p minus 1 times mc squared. Now the relativistic kinetic energy is very nearly 1/2 mu squared when u is less than c. And as the figure shows, it differs significantly from the classical value at very high velocity. It actually approaches infinity as u approaches c. So here's the Newtonian version of this. Here is the relativistic version. So this says kinetic energy approaches infinity as u approaches c. No particle with mass can be accelerated to the speed of light. This does not apply to space itself. Space can travel faster than light. If you're interested in that, Astronomy 111. Okay, an electron has a rest energy of 1/2 MeV. An electron traveling at 0.968 c has a gamma p of 4. The electron's kinetic energy is 1.5 MeV. Kinetic energy is gamma p minus 1, that quantity times epsilon naught. So gamma p is 4, so it's a quantity 4 minus 1, which is 3, times 0.5 MeV, so 1.5 MeV. In this case, the electron has 3 times the amount of kinetic energy as it would have of mass energy. Now, this is a triangle that shows the convenient way to remember the relationships between velocity, energy, and momentum of a particle. You don't have to memorize anything. You can copy this down. So we're going to calculate the rest energy and the kinetic energy of a 100-gram ball moving with a speed of 100 meters per second, and an electron with a speed of 0.999 c. The physics of this is kinetic energy, relativistic, and rest energy. The knowns and unknowns for the ball are mass equals 0.1 kilograms, v equals 100 meters per second. We need to know the rest energy and the kinetic energy. The ball is non-relativistic, so E naught is just mc squared, and k is 1/2 mv squared. For the numerical solution, E naught equals 0.1 kilograms times 3 times 10 to the 8th meters per second squared. And that ends up being 9 times 10 to the 15th joules. That's relatively large because it has a fairly large mass. The kinetic energy is 1/2 mv squared, or 1/2 times 0.1 kilograms times 100 meters per second squared. This ends up being only 500 joules. This is typical kinetic energy for an ordinary object. The ball has a very large rest energy because it has a relatively large mass, but it isn't moving very fast, so the kinetic energy is relatively small. Now we're going to tackle the speedy electron. We know the mass of the electron is 9.11 times 10 to the minus 31 kilograms. The speed is 0.999 c, and we need to know the rest energy and the kinetic energy. The electron is relativistic, so E naught equals mc squared. K equals the quantity gamma p minus 1 times E naught. And of course, gamma p is the Lorentz factor of 1 over the square root of the quantity 1 minus beta squared. The algebraic solution is E naught equals mc squared. Kinetic energy is the quantity gamma p minus 1 times epsilon naught. We can plug in for gamma p. It'll be the quantity 1 over the square root of the quantity 1 minus u squared over c squared minus 1, all times epsilon naught. Okay, so now we can start plugging in numbers. Here's our mass for the electron, 9.11 times 10 to the minus 31 kilograms times the speed of light squared, so the E equals mc squared. This ends up being the rest mass energy, the rest energy of 8.2 times 10 to the minus 14 joules. The kinetic energy then is the quantity, this quantity here, 1 over the square root of the quantity 1 minus 0.999 squared minus 1, all times 8.2 times 10 to the minus 14 joules equals 180 times 10 to the minus 14 joules. Unlike the ball, the speedy electron's kinetic energy is relatively large compared to its tiny rest energy. That's because it is moving very quickly and its mass is extremely small. The figure below shows two balls of clay of equal masses m and an equal initial kinetic energies k, which slam together in a perfectly inelastic collision to form one larger ball of clay at rest. The kinetic energy is not conserved, but the total energy is conserved. In order to conserve total energy, the mass of the clay after the collision must be slightly greater than the mass before. Now, the mass before was just 2m. The mass after is 2m plus 2k over c squared. This is the kinetic energy that has been converted into mass. So what this is saying is that E equals mc squared. Energy and mass are equivalent. Mass is just a concentrated form of energy. Energy can be converted into mass, and mass can be converted into energy. Now we're going to talk about mass energy conservation. You may have heard of conservation of mass, and you may have heard of conservation of energy. But now we recognize that mass and energy are two animals of the same type. In other words, mass is energy and energy is mass. They can be converted between one and the other. The figure shows a typical experiment done on a particle accelerator. An electron with a relativistic speed hits a target electron. Particle-antiparticle pairs of new particles are created out of this energy of the collision. Now, if a particle meets its antiparticle, they will annihilate, creating pure energy in an amount equal to their combined mass energy. Now, back in the early days of the universe began as a tiny, incredibly dense speck of pure energy. It expanded, cooled, and matter and antimatter were created out of the energy. Now, normally, you will create an equal number of particles of matter as you do antiparticles. But in the early universe, for every 1 billion of antiparticles that were created, 1,000,000,001 particles were also created at the same time. That 1 in a billion particles of ordinary matter became the universe that we know and love today. So we owe our existence to the fact that for every billion of antiparticles that were created, 1,000,001 particles of ordinary matter were also created. The photo to the right shows that the tracks of elementary particles in a bubble chamber during the creation of an electron-positron pair. The negative electron and positron spiral in opposite directions in the magnetic field. Mass may be converted into energy, and energy may be converted into mass as long as the total energy is conserved. So the law of conservation of total energy states that the energy E is the sum of all the energies of all the particles in an isolated system, and that is conserved, or EI equals gamma pi mi c squared, and that's the total energy of particle I. The figure below shows an electron colliding with a positron, its antimatter particle, and the two annihilating each other. The electron and positron have the same mass, me, but opposite charges. And the positron, of course, is an antimatter of the electron. Conserving both energy and momentum in the annihilation of electron and positron requires the emission in opposite directions of two photons of equal energy. A final total energy of the two photons is EF equals 2 photon, or approximately equal to 2 times MEC squared. Of course, this is the rest mass here, which corresponds to an energy of 0.511 MeV for photon, which is gamma rays. Now, why do we need two photons? Well, this momentum is zero here. The initial momentum is zero, and momentum has to be conserved. So the only way you can get momentum to be conserved is remember, light has momentum. You have two photons coming off in opposite directions with the total energy that combines to make the mass energy of the two particles that have collided. A proton has a rest energy of 938 MeV. A proton and an antiproton are each traveling at the same slope, so gamma p is much less than 1, speed in opposite directions. They collide and annihilate. What is the outcome? The outcome must conserve both energy, which has a total energy of 1876 MeV, and momentum has to be 0. So you have a choice here. You have this one, or this one. And then A or C, or A, B, or C. Okay, so we look at each one individually. In A, total energy is conserved because if you add these two together, you end up with 1876 MeV. Momentum is conserved because the photons move off in opposite directions, and light has momentum too. So in other words, this might be negative momentum that is an equal amount of positive momentum. Energy is conserved in part B, but momentum is not conserved because momentum is a vector. In C, total energy is conserved because you have three of them of 625.33 MeV, and that equals the total energy of 1876 MeV. And momentum is also conserved here because the photon momentum in the y direction is going to cancel itself out, and the photon momentum in the x direction would do so too. So the correct answer to this is D, which would be A or C. Probably the most well-known application of conservation of total energy is nuclear fission. And in nuclear fission, a uranium-235 nucleus absorbs a neutron and then quickly fragments or splits and fissions into two smaller nuclei and several extra neutrons. The mass has been lost and converted to an equivalent amount of kinetic energy in the fission products. This generates heat, which is used to generate steam to run turbines and generate electricity. Now, the other side of this coin is fusion. And the most common place to find fusion is in a star. The closest star to us is the sun. In the core of the sun, the temperature exceeds 15 million Kelvin and the pressure is very high. High temperatures imply that the nuclei in the core are moving very fast, and the high pressure is pushing them together. So the high speeds in the nuclei, due to this high temperature, allow them to overcome the electrical repulsion of protons to collide. That is, they have to come within 1 times 10 to minus 15th meters. At that point, the strong force takes over and the nuclei fuse. The 0.72% difference in mass between the reactants and products is released as energy, V equals mc squared. So here at low temperature, the electric repulsion is high enough to keep these two hydrogen protons apart, and there's no fusion. But at high temperatures, the particles are moving fast enough that they can actually approach within 1 times 10 to minus 15th meter. The strong force takes over, and the nuclei fuse. Okay, now the sun, like all small stars, uses the proton-proton chain to fuse 4 hydrogen into 1 helium. If you're curious about this, here's the details of the proton-proton chain. I'm not going to go over this, but if you're interested in this, Astronomy 111, and it's pretty cool. So how much hydrogen does the sun burn per second? The luminosity of the sun, including that of neutrinos, is 3.9 times 10 to the 26 watts. That's its power. The sun's fusion reaction converts 4 hydrogen nuclei with a combined mass of 6.693 times 10 to the minus 27 kilograms into 1 helium nucleus with a mass of 6.645 times 10 to the minus 27 kilograms. How much hydrogen needs to be fused into helium per second to supply this energy? The physics of this is energy balance, fusion, energy mass equivalence. We know that the power of the sun is 3.9 times 10 to the 26 joules per second. The mass of 4 hydrogen, that is the reactants, is 6.693 times 10 to the minus 27 kilograms. The mass of the products, which is the helium, is 6.645 times 10 to the minus 27 kilograms. The speed of light is 3 times 10 to the 8 meters per second. We need the mass rate of hydrogen into helium. The equations are the power from fusion equals luminosity, equals mc squared equals the mass loss rate times c squared. Each reaction converts 6.693 times 10 to the minus 27 kilograms of hydrogen into 6.645 times 10 to the minus 27 kilograms into helium. The 0.7% difference in mass is converted into energy. So the mass loss per reaction is the 4 hydrogens. That's the 6.693 times 10 to the minus 27 kilograms of hydrogen per reaction. minus the products, which is the one helium, that is minus 6.645 times 10 to the minus 27 kilograms of helium per reaction. The mass loss per reaction, that's what's converted into energy, V equals mc squared, is 0.048 times 10 to the minus 27 kilograms per reaction. So the energy per reaction, E equals mc squared, is this mass, 0.048 times 10 to the minus 27 kilograms per reaction times the speed of light squared. It ends up being 4.32 times 10 to the minus 12 joules per reaction. So the number of reactions per second is 3.90 times 10 to the 26 joules per second divided by 4.3 times 10 to the minus 12 joules per reaction. You can see the units cancel out, and you wind up with 9.03 times 10 to the 37 reactions per second. Okay, so each reaction consumes 4 hydrogens, so the rate of hydrogen burning is 6.693 times 10 to the minus 27 kilograms of hydrogen per reaction times 9.03 times 10 to the 37 reactions per second. So that is 604 million metric tons of hydrogen per second. This produces helium at a rate of 6.645 times 10 to the minus 27 kilograms of helium per reaction times 9.03 times 10 to the 37 reactions per second, or 600 million metric tons of helium per second. And the mass loss rate, which is what is converted into energy, is 0.048 times 10 to the minus 27 kilograms per reaction times 9.03 times 10 to the 37 reactions per second, or 4.3 million metric tons mass loss per second. In other words, the sun takes 604 million metric tons of hydrogen per second, converts it into 600 million metric tons per second of helium, and loses 4.3 million metric tons of mass that gets converted to pure energy to produce the luminosity of the sun, which is 3.9 times 10 to the 23rd kilowatts. So this is the sun's energy bill right here. And by the way, that is 4.7 million US tons lost per second. Now this right here is the first ever picture of the core of the sun. It actually shows the neutrinos coming from the fusion reactions in a core. Now, one product aside from energy of the proton-proton chain is a neutrino. It has very low mass, very high energy, and it passes through matter very easily, so it's hard to detect. There are billions of them passing through your body right now. The first experiments measured only 1/3 of the predicted neutrinos, which was pretty scary. I still remember this. They were worried, was the sun not working correctly? Was there something wrong with the reactions in the core? Weren't there enough reactions? Because very bad things happen to stars when their fusion reactions shut down. Because the thing that holds up the star against the crushing grip of gravity is the energy generated by fusion. If the fusion reaction shuts down, the star collapses, and that's really bad. We were hoping that our models were wrong. Well, it turned out, fortunately, we were wrong. Fortunately, it was found that neutrinos could spontaneously convert into 3 types as they traveled to the Earth from the sun, but early detectors were only able to detect one kind and were missing the other 2 kinds. More recent neutrino measurements on Earth now confirm that our models of fusion in the sun's core are correct, and the sun is not going to collapse anytime soon. So we dodged that bullet. Now for a recap of Galilean relativity. Galileo noticed that the speed of a thrown object depends on how fast and in what direction the thrower is moving. If the thrower is moving in the same direction as the throw, the projectile goes faster with respect to the ground. If the thrower is moving in the opposite direction, the projectile goes slower with respect to the ground. In other words, velocity is had as vectors, and stating your reference frame, that is your rest frame, is still absolutely vital. Now, Galilean relativity does not work for light or for anything moving at relativistic velocities. You can't just add velocities up. If Galilean relativity worked for light, we would expect to see the light from a star in orbit around another star to arrive at different times, depending upon the velocity of the star. So for instance, we have a binary star system here. We have one star in orbit around another one. The Earth is off to the right here somewhere. When the star is approaching the Earth in its orbit, we would expect to measure the speed of light as greater than 3 times 10 to the 8th meters per second if Galilean relativity worked, because the velocities would just add. When instead the other star is receding from the Earth in its orbit, we'd expect the speed of light here to be measured as something less than 3 times 10 to the 8th meters per second. We never see either one of those things. We don't see anything but the light is always traveling at the same speed, 3 times 10 to the 8th meters per second. What we see instead is a Doppler shift in wavelength and frequency that is due to length contraction and time dilation. In other words, the speed of light is a true physical constant. This is a picture of the Michelson-Morley experiment. These two scientists devised an experiment to detect the motion of the Earth through the ether. The ether was a medium proposed to allow light to travel through the vacuum of space, sort of the way that air allows sound to travel. Light should move at different speeds in the direction of the Earth's motion through space and the ether than it does in different directions. But they detected no difference in speed. That means there is no ether and the speed of light seemed to be a constant, and light travels just fine through a vacuum of space. All experiments since then have verified this. Now here's the Lorentz factor plotted against the speed. The Lorentz factor describes the amount of contraction and the slowing of clocks. At slow speeds, the effect is very small. It's essentially equal to 1. But as the speed gets closer and closer to the speed of light, the Lorentz factor approaches infinity. Time dilation and length contraction are democratic. So here we have an observer on Earth, and this observer is watching a spacecraft go by. Spacecraft is moving at 87% of the speed of light. The Lorentz factor is 2. So to an observer on Earth, the spacecraft clock appears to run slow, and the ship looks shorter in length. So ship looks short at half its normal length, and from Earth, the clocks on the spacecraft appear to be taking 2 seconds for 1 tick. So they're running twice as slow. That's the Lorentz factor. To somebody on the spacecraft, the Earth is the thing that's moving at 87% of the speed of light. So the Earth appears to be half its normal width, and from the spacecraft, the Earth's clocks on Earth appear to take 2 seconds for 1 tick. Each observer sees his own shape and clocks as normal, and the other guy's shape and clocks as whack. These effects have been verified many times. Now, time and space are relative. They are not separate from each other, but they're intimately linked. We refer to this as four-dimensional space-time. But the speed of light is the same for everyone. Everyone sees themselves as normal, and the other guy is squished in length and with slow clocks. So there's 2 principles of special relativity. The laws of physics are the same for everybody, regardless of the constant velocity at which they travel. Constant velocity means inertial reference frame. No acceleration. Can't turn, change direction, can't change speed. Regardless of the speed or direction of travel, the speed of light is always the same for everybody. Now here's some possibilities for space travel. We have an example. Spacecraft is leaving the Earth, heading for a star 70 light years away, traveling at 99% of the speed of light, which is the Lorentz factor of 7. To an observer on the Earth, it takes the spacecraft 140 years to get the star and back again. They're traveling at nearly the speed of light, and they're traveling a total distance of 140 light years, so that'll be 140 years. To the passengers on the ship, it only takes 1/7 as long, time-wise, that is 1/7 through the Lorentz factor of 7. So that's 20 years due to time dilation for the round trip. And for them, the star is only 1/7 the distance away due to the Lorentz factor of 7. So 1/7 of 70 is 10 light years away because of length contraction. Now, this sounds absolutely wonderful. You wouldn't age very much. You'd age 1/7 as fast as the rest of the universe. For most people my age, so we would really like this. But it always comes at a price. The price is you would need extremely good shielding to protect against starlight that is Doppler shifted to gamma rays. So starlight would be lethal. And dust grains hitting you with relativistic speeds and energies. So it'd be like getting a stone hit your windshield with the force and the energy of an atomic blast. You would need hugely powerful engines and or lots of fuel to give you the kinetic energy necessary. On top of that, when you come back, all your friends and family would be dead. High-speed travel to the stars is possible, but it comes at the cost of friends and family. You can travel into the future, but it's a one-way trip. You can't come back again. Time travel into the past is impossible, which is fortunate because you could go into the past and kill your grandfather, and then you would kill yourself. Thank you.